Hey, awesome P-Calc students. Alright, so for this video, we are going to start 4.1. The title of section 4.1 is Polynomial Functions and Models, okay? Models just meaning that we are going to do some application problems with the polynomial functions that we are going to study. So, a couple of vocabulary here. The first one is called polynomial function. Defined is a function of the form. Okay, so this is going to be a long one, so I'm just going to put it down here, okay? F of x equals a sub n. So notice how the subscript is way below the letter a times x to the exponent of n plus, so this is my first term. Term number 2 is a sub n minus 1 times x to the power of n minus 1 plus dot dot dot. Okay, that means I can have as many terms in the middle or in between as I wish. And then we have a subscript 1 times x. And technically this one should have a power of 1. But power 1 is the same as just no power here, so we're just going to leave it x. Okay. And then our constant term, which is a subscript of 0. This one doesn't have any x, so this is my constant. So the a values are the leading coefficients, okay? The x is obviously your variable, your input. And then the n, okay, these are all exponents. Okay. Where a sub n, comma, a sub n minus 1, dot dot dot, a sub 1, and a sub 0 are real numbers, okay? Because they are leading coefficients, they could be any number they want. Oops, let me just zoom in a little bit, okay? Any number they want except imaginary, okay? So we define all the a's, the leading coefficients, okay? And let's define n, our real numbers, and n, so this is an n, this is our next power over. So n, since it's an exponent, it's a non-negative, okay, non-negative. And it can't just be any numbers, it has to be integers, okay? So non-negative integer. Okay. Integers are numbers that could be, usually they're positive or negative whole numbers, but because right here we said non-negative, so now we're just really talking about positive whole numbers, okay? So that is our definition of a polynomial function. Now let's talk about the domain of all polynomial functions. Domain, it's always all real numbers. Doesn't matter what the polynomial function is. If you say that this is a polynomial function, then the domain is all real. Notice I'm not giving you a range because the range will be different, okay? Okay. The degree of the polynomial is the largest power of x, okay? And we're going to look at a couple examples of what the degree may be. Alright, moving on up, here we go. I'm giving you some examples of polynomials and non-polynomials. Here we go. First one, let me give you an example of a polynomial. F of x equals 2 minus 2x to the 4th. Okay. Well, let's look at it. Currently, this is not written in descending order. I normally would like to write it to where the power, the highest power is first. So negative 2x to the 4th should be first, and then positive 2 should be second, okay? So when you see stuff like this, rewrite it this way. So look at the leading coefficients, okay? Which earlier we said a were the leading coefficients. This is an a, this is an a, okay? That means since we're writing it over, that's also a. Since they're real numbers, we're good. Remember, they can be negative or positive, anything we want to be. Then we're going to look at the powers, right? We only have one power here, and it's a non-negative. That means it's positive, and it's a whole number, so we're good. So this is a polynomial function. Let me give you a non-polynomial function. Y equals x squared minus 2 all over x to the third minus 1. Okay. This is a non-polynomial. Okay. The reason that this is a non-polynomial is because, let's look at this really quickly. If you think about this, okay, I would have, if I were to reduce it, okay, I would have if I were to write this right here on the top, I would have a negative exponent on the top, right? So any degree or any power that you have on the bottom and you want to write on the top, would you agree that you make it its opposite, which is negative? So right away, the power, okay, is not a non-negative. In addition, because this is a ratio of two polynomials, okay, the reason, because it is a ratio of two polynomials. Okay. That is why this is not a polynomial, because it's a ratio of two polynomials, and the ratio means a fraction. Okay. Let's give you another one that could be a polynomial. How about this one? F of x equals, make up something, negative 10 x to the third times x minus 3 to the 6. Okay. All right, let's check this out. Currently, does it look like this, separated by an addition or minus? Okay. Not really. It has these two factors right here. But if you wanted to, you can distribute. Okay. We can distribute the negative 10x to the third times x is going to be a negative 10x to the... Oh, I lie. I can't distribute. I have to multiply this out 6 times. Oh, don't do that. Okay, so currently this, I can't distribute this. Well, I can. It would just take too long. But because this is, if I were to FOIL this out, I will have 7 terms, okay? And distribute by negative 10x to the third. So technically, I will have a polynomial with 7 terms total. And because, you know what, let's look at the degree as well. Notice how when I write it in order, okay, this has a degree of 4 because that is the largest power of x that I have. This one doesn't have any power. This one should have a degree of, are you ready? If I were to sit here and multiply it out, my very first term should have a power of 6. Okay? So, and I don't need to worry about anything else when I'm talking about the degree, because I only need to worry about the largest power of x. So the term with the largest power of x. So this is at the power of 6, x to the 6, when I FOIL out all 7 of them. But negative 10 x to the third times x to the 6, when you are multiplying numbers with the same basis, because x and x are the same basis, I can just add the exponents. So 3 plus 6, this will give me a degree of 9. Okay? And you can have a degree when it is a polynomial. If it's not a polynomial, you don't have to worry about having a degree. All right, so over here, non-polynomial. Y equals square root of x. Okay? And the reason that this is not a polynomial, because when I want to rewrite it, square root of x is really x to the power of a half. Okay? Because x is the power of half, well, half is positive, so that's true, but it's not an integer. So therefore, this is not a polynomial. Okay? All right, one more. A polynomial, what can I make up? How about this? Y equals to 0. Is this a polynomial? Sure, it's a boring one. It's a constant, okay? But I can make up stuff. So y equals 0, x to, let's say, the 4th, plus 0, x to the 3rd, plus 0, x plus 0, right? these are still coming out to be 0. So technically, y equals 0 is a polynomial with a very boring degree, actually. Okay, so if I really wanted to, I can also do this. Y equals 0x. Okay, to the 0 power. So all of these is still going to be becoming 0. So this has, it doesn't have any x with it. Okay, if I just want to write a constant. So a constant function, it's still a polynomial function. It's just a constant one. It has a special name. But it still has a degree. Any constant will have a degree of 0. Okay, because any base to a 0 power is 1. 1 times 0 is itself. Okay, so with that said, let me give you one more example of non-polynomial. How about this? Y equals 1 over x. This is not a polynomial because if I were to rewrite it, this will give me x to the negative 1. And remember, there's an issue because all of my exponents, all of my n, has to be non-negative. This is a negative number, so therefore that's going to give me an issue with being a polynomial. So all three of these are non-polynomials, and pretty much anything that doesn't have a fractions or negative exponents, that will give you a polynomial. Okay? Now, what do they look like? If I give you a graph, and I said, hey, tell me which one's a polynomial and which one isn't. A graph of a polynomial will be very smooth, okay? Very smooth. It needs to be continuous. So smooth and continuous. Okay? That means I can't pick up my pencil. That means I need to graph it from beginning to end without picking up my pencil. Now, if I give you a graph, you can tell me if it's that the graph itself, the function itself, is a non-polynomial if it has gaps, okay? If it has holes, okay? If it has corners, or if it has any cusps. Okay? So if I have any one of those four, then the graph is no longer a polynomial. Okay, just feel free to hit pause if you need to finish writing, because I'm flipping over. Okay, so the next definition on this one is a power function of degree n. Okay, so power function, it's a monomial function, so it's only one term. So power function of degree n is a monomial function of the form f of x equals a times x to the power of n, okay, where your a term, it's a real number, just like the definition of a polynomial. And a can never ever be 0, because if it's 0, then I don't have a, then it's just going to be a constant, okay? And a can never be 0. And in addition, okay, your exponents, just like the definition of a polynomial, need to be greater than 0 and an integer. Okay? So it's still the same definition as your polynomial. It's just now I'm only going to use the very first term. So I'm going to put aka, look at that, different color. Aka power function is the first term, the entire term, when it is written in descending order. Okay, that means from highest power to lowest power. So let me give you some examples, i.e. f of x equals, let's give you, making up something here, negative 6x to the 9 plus 4x to the 4th minus 3x squared and plus 100. Okay? So first, is it a polynomial? What you need to check for are the exponents. Are these all positive and are all of them whole numbers? If they are, you're good because a can be anything they want to be. The constants, the leading coefficients, okay? So let's talk about the degree of this term, this polynomial. The degree is the highest power of x. Because this is already in descending order, the highest power of x is 9. So the degree is 9, okay? Then I want to talk about the power function of degree n, okay? And in your book, power function, it's also known as, is aka n behavior. Okay, so you're going to see both and they mean the same thing. And the n behavior, if you look at this, it's a function. The power function is a function, so don't forget the y equals. Okay, and it says it's a monomial function. That means I have one term. Okay, so one term, and the largest term, okay, the first term when it's already in descending order is simply negative 6x to the 9th. Okay, so the power function is when you take the entire term. The degree is only when you are taking the exponent. Okay, so let's look at some properties of power functions. Okay, f of x equals x to the nth, where n is an even integer. So, i.e., y equals x to the 4th. Let's look at this graph. Okay, x to the 4th, since I'm out of space, let's move it down here. X to the 4th, let's make a chart really quickly. When x is 0, y is 0. When x is 1, y is 1. When x is negative 1, negative 1 to an even power is positive. So if I really need to sketch this out, excuse me, 0, 0, 1, comma 1, and it looks like this. There you go. Yes, it looks like a parabola because it's just the same as the parabola, except that it shoots up a lot faster because you have a larger exponent. So part 1. F is an even function because look at the symmetry. It is symmetric about the symmetric about what? About the y-axis. Okay. Because it is a polynomial, the domain is simply all real numbers, okay, based on our definition of a polynomial. The range, the smallest value is 0, and it shoots all the way up. So we are including 0 all the way to positive infinity. F always contains 3 points. What are the 3 points? 0, comma 0, 1, comma positive 1, negative 1, comma positive 1. The inputs, it can be any number you want to choose, but the outputs, okay, they will always be positive because any number raised to an even exponent will always be positive. And it doesn't matter what this exponent is, as long as they are even, these are the 3 points that you always have. As n, remember n is your power, okay, so n is your power. As n increases, the graph blink more rapidly, okay, the graph means also increases more rapidly when x is either less than negative 1 or x is greater than 1. So that means is this, when I put in a value of 2, well, if I have a power of 2 up here, 2 squared is only 4. But when my power is large, like 4, 2 to the 4th, it's actually 16. So notice how the larger the exponent, the faster it increases when x is not between -1 and 1, when x is greater than 1 or less than -1. But for x near the origin, that means near 0, 0, the graph tends to, it flattens out. Okay, so it tends to flatten out and lies closer to the x-axis. Okay, and let me just give you a picture of what I mean by that, by calculator format. Okay, so what I'm going to compare for you is clear it out and highlight my plot. I'm going to compare x to the 10th power and x squared power. Okay. Let's make my window from -4 to +4, -4, +4. Okay, so the first one we graphed with x to the 10th, and then the second one was a x squared. Okay, so notice how it says here, as n increases, so notice how this U, very U-shape-ish, is my x to the 10th. Notice how it shoots up so fast, okay? And it increases more faster, okay? As x, it's approaching something larger than 1, or something smaller than -1. But here's an interesting piece. But near the origin, which is this piece right here, okay? The graph tends to flatten out. That means when x is to the 10th, notice that I'm very much closer to the x-axis. And let's zoom in really quick. So let's go when y is -1 and +1. Okay. So this is my x to the 10th. And then this is my, okay, so x squared. So notice how it's not as flattened out to the x-axis as my x to the 10th. So that's what they mean. Okay. And you guys know why it's so flattened out? Okay. So let's compare y equals x to the 10th and y equals x squared. Okay. So let x be, let's just say 1/2. Okay. So when x is 1/2, x to the 10th, here we go. Okay. 1 divided by 2 to the 10th power, 9.765625 e to the -4. That means this is 10 times 10 to the -4. If I move this over 4 decimal places, this is 0.0009. Okay, so that's how small that is, really small. Versus if I take 1/2 and I square that, that's a quarter. Then I'll show it to you. 1 divided by 2 squared. So this is 1.25, which is a quarter, but this has 3 zeros in front of it. So notice how this is so much smaller, because the output is so much smaller when x is between 0 and -1. That's why when you graph it, it's so much closer to the x-axis if the function itself it has a high exponent. Okay. Then now we're just going to fill out this chart, which is when n is an odd function, which is, let's talk about y equals x to the 3rd. And I'm just going to say it, and your job is to fill it, okay? Because I want you to listen and not just copy without listening. So when n is an odd function, which is this piece, we all know what this looks like, okay? This is what y equals x to the 3rd is. F is an odd function, which we know, which is symmetric about the origin. Okay, so this is the spot where you spell out symmetric about the origin. The domain and the range, they are both all real numbers. So write all real numbers on there. And F always contains 3 points. First point is when x is 0, 0 to the 3rd is also 0. So 0, 0 is one of them. When x is 1, 1 to the 3rd is 1. So 1, 1 is also another one. When x is -1, -1 to the 3rd is still -1. So those are your 3 points. Okay. And number 4, it says here, everything is the same as when it's even. So the only differences we have are the first 3 main points of the box. All right, this is going to be the end of video notes. I hope you fill those out and have a wonderful day.